let me share my content as usual. Hold on. Conductor. Okay. Okay, can you see the slides? All right then. Okay, assalamualaikum, good morning. So let's get started with our course. So welcome to your 4th year. Are you excited to be in the 4th year? Ataupun tak ada perasaan pun, sama aja. You're in your final year already, right? So 4th year, first semester. Intern. Okay, we're going to talk about that, no worries. I'm going to share with you some exciting news as well, because we have quite a number of expansion in the neighborhood as far as industry is concerned. And we've also received a request from Singapore for our students, especially applied physics and other engineering students. Okay, so I'm going to share with you a little bit later. So this is ZAT487, as you know it, semiconductor fabrication processes. Let's recap. In the last semester, you have learned about physics of semiconductor devices in ZAT487. So where you've learned all the fundamentals, right? The theories behind the physics of semiconductor materials and physics of devices. We've covered quite a number of devices as well in our previous course. So those serve as a strong fundamental for you before you learn this course, right? So that's what you've learned. So in this course, as the name explains, right, semiconductor fabrication processes. So you're going to learn about the fabrication of the devices. Okay, so in the last semester you learned about the fundamentals, the theories behind the operations, and multiple modes of operation. For example, if you talk about CMOS, then in this course we're going to learn on how do we actually fabricate the devices. Okay, so the focus of this course will be given to integrated circuit or transistors in particular, but all the processes that you're going to learn in this course, we're going to see later on a range of different processes are also applicable to some other semiconductor devices as well. So all in all, if you learn the fabrication processes on integrated circuits or transistors, some other devices can be fabricated with even simplified process. Okay, so kiranya proses untuk fabricate integrated circuit ni is a very complete and a very long and a very complicated process, tapi you can just extract the very same processes here and there to fabricate, for example, solar cells, LEDs, solid state drive, and some other devices as well. Okay, so as long as you learn IC fabrication, you should be able to adapt the very same process for other devices. Okay, so when we talk about IC fabrication, we normally associate the industry we're going to see later on in a bigger picture. The industry will be wafer fab, okay, wafer fabrication, or we also call it wafer foundry. Tapi in short, we normally call it wafer fab lah. Kat Malaysia, we normally call it wafer fab. But some call it wafer foundry, some call it front-end semiconductor fabrication. But in short, it's called wafer fab, at least in Malaysia. So if you see the picture down here, it is a picture of a wafer with integrated circuits printed on the wafer. So you can see here, the wafer is roughly about 8 inch in diameter. So that's about 200 mm from there to there in diameter, or 20 cm if you like, if you want to convert into centimeter. So so each of this, you can see each of these square or block, if you like, is an integrated circuit. It's a chip. But in this single chip, it may contain up to millions or perhaps billions of transistors that we've learned in 386, okay, in the previous semester. So this is only one example. So it really ranges from different looks and different sizes and everything. It really depends on what the customers need to print on the wafer. So we're going to learn it on. So if you zoom this in, you may see something like this. So for example, this you can equate this single square with a single chip, for example, and then in this chip later on, we're going to see that you have millions or up to billions of transistors, depending on which process technology are we talking about. So one example, if you look at Apple, kalau buka iPhone, kalau if you look into Apple A8 chip in iPhone, so the line width means the line punya lebar line lah. So we're gonna see later on in the YouTube video. So if you zoom into this, okay, if you zoom into this, if you go inside, so you're gonna come down to a basic building blocks. Okay, a basic building block. Macam bangunan, kalau you jalan, I explained this in our last course. If you are walking through a city, you're gonna see different buildings around you with different height, different width, perhaps different shapes. So this is pretty much what you're gonna see if you see the cross section of the circuit from the side, from the cross section, from ASML. So if you are here, for example, then you can see that this line width, the width of this road, if you like, is about 15 nanometer wide. Okay, width is 15 nanometer. And then the overlay here, you talk about this overlay, don't worry yet, we're going to come back to that in lithography process, is the alignment that you have to do when you print the current circuit on the previous circuit, the current layer on the previous layer. Okay, dia kena ada alignment lah, macam you buat pilar rumah kan, pilar rumah you have to align tingkat satu dengan ground floor kan, kalau tidak dia jadi sengit, right? So you have to have a very precise alignment when we talk about building a chip. Okay, so this advanced chip technology, for example, if you talk about 15 nanometer, can only be fabricated by using EUV lithography system. EUV lithography is actually a process, one process that you're going to use to fabricate a chip, just like a typical printing process. So normally, I normally give an analogy of printing your T-shirt, for example, with any name, kan, nama ke logo ke whatever. If you want to print, you want to print a specific shape, specific size, specific whatever. You have more different parameters for you to do the printing. So the same goes to the printing of the circuit as well. So in this case, when you want to print an integrated circuit or thousands or billions of transistors, you want to print them in with the specific size, dimension, alignment, and everything. Okay, and the printing of the circuits is called lithography process that we're going to learn later on. So one of the main or one of the key processes in a semiconductor fabrication. So let's just go out here for a while. This sorry, so we just unshare this. Okay. Let me share with you the YouTube. YouTube, yeah. I go to YouTube video. Okay, can you see the YouTube? About? Okay, good. So let me just rewind this. Okay, so let's zoom in into this particular chip. See the very same structure that we talk about is now. So that's the chip A8 in iPhone. So you have a range of different sub devices there. So if you take one area of the wafer, one chip, you zoom into the wafer, zoom into the chip. So you'll see the basic building blocks of the chip. Okay. So ini yang structure yang saya share in the slides tadi. So that's how you can actually imagine. So let's look at it once again. Take the chip, open it up, zoom into one area on the wafer, one chip on the wafer, and then zoom into the chip. Okay, so you can see that, right? So in this course, you're going to see how do we actually fabricate these features, so these structures on the wafer, okay? So you're going to see later on in the next 14 weeks or so. Let me go back to my slides. Right. Okay, please confirm if you can see the slides, just in case. Is it okay? All right, good. So let's move on. So it's a bit more started. Something's wrong, battery, I think. Okay, if you look at other chip design, for example, if you look at Kirin from Huawei, 990 5G, right, for 5G chips. So the CD, the critical dimension, the line width of the features that we saw just now in the previous slide, is only about 7 nanometer. Right? 7 nanometer is very, very small. So if you want to compare, our hair is like 100 of micron thick. So this like you slice 1,000 more to get into nanometer, and then you slice, you slice more, right? Slice more to get down to about 7 nanometer. So that's very, very thin. So this is based on TSMC's 7 nanometer process. So TSMC's is the king of the wafer fabrication at the moment in the world, right? So it stands for Taiwan Semiconductor Manufacturing Corporation. So it's located in Taiwan. So they are now the number one for wafer fab in terms of the technology, the capability. So most of the state-of-the-art or advanced chips that we have now in the laptop, in the phones, in the tabs, in the whatever latest gadgets. So most of the chips are actually fabricated in TSMC or by TSMC. Okay, so it's using EUV system or extreme UV. Kita belajar sebelum ni sampai UV, right? UV, and then if you go down further, you're gonna see deep UV. You're gonna go down further. You're gonna see UV, UVC, UVB, and then if you go down further, you're going to go down to extreme UV. So the wavelength of the illumination from the EUV system is about 10 to 14 nanometer. Okay, maksudnya wavelength kita guna untuk print the chip, so the circuit, so is only about 10 to 15. So to be precise, it's about 13.5 nanometer. And this, so this is the chip in the middle, and this on the right is the EUV system. So try to compare that with our BT, if you like, blade tutorial. So the engineer or the operator is here. You can see the size of the operator. Ini dekat IBM. Yep. Okay, hold on. If you can see the size by IBM, so the people here, you can see the people here. Kecil je kan? So you can see the height there is more or less double of the engineers, for example. If that guy is about 1.8, so the UV system is easily 4 meters perhaps in terms of height. So if you see the width, so it's more or less about 3/4 or almost one, the exact size of our BT. Bilik tutorial. Kalau if you are in BT 157 or 146 perhaps, so lebih kurang size tu lah. So that is a one single equipment. So typically for one fab, for lithography process, you need to have at least 20 of those, right, to run mass production. Okay, so if you talk about Kirin 990 chip, so it contains about 10.3 billions of transistors, right, in 200 mm area. So in such a small area, you have 10.3 billions of transistors. So enabled by EUV lithography process. Of course, it doesn't depend only on EUV process, but we have some of other different processes as well to realize the chip. But one key process for the fabrication is called lithography. So the printing of the chip using light. Okay, kita pakai light. So if you talk about Silterra, this is the inside of Silterra. So the capability of Silterra is down to about 100 nanometer. Okay, Silterra capability is only down to 100 nanometer. So that means if you want to print circuits below 100 nanometers, Silterra cannot do it. Kenapa? Why do you think Silterra cannot do below 100? Anyone? Kenapa tak boleh buat? You can type or you can unmute yourself. Lama tak ada suara ni. Why do you think Silterra cannot do below 100? Hardware limitations, okay? Good. Hardware limitation. Any specific limitation of the hardware? Yeah, the answer is yes, hardware limitation. But do you have anything to elaborate, Haziq? Which process do you think is the limitation? Yeah, exactly. The EUV, right? We just discussed about EUV. So the printer lah, dia macam printer lah, but it's not exactly printer, but EUV is responsible for the printing process. So Silterra tak ada up to down to, I'll probably say down to EUV. EUV is super sophisticated, super expensive. Silterra has, nanti kita akan explore this further. For the printing process, let me just brief you what Silterra has at the moment. So Silterra has an eye-line illumination. Ni illumination system. So kita just brief dulu. Eye-line is 365 nanometer. Then Silterra has DUV, 248 nanometer. When else, before I left back in 2000, back in 2000. The third one, let me just write down here, ARF, argon fluoride. This is 193 nanometer. So this is the lowest that Silterra has, the illumination, right? So to be able to print the feature size, so you need to have dia punya wavelength of illumination there is usually about double, not exactly, but about double. Kalau you ada down to 193 nanometer illumination system, so that can print down to about divide by 2 lah, 193 divided by 2, so that's about 100 nanometer with decent resolution. So like bila kita nak print line tu, you want it to be with good resolution, right? You don't want it to be blurry and zigzaggy. You want it to be a very fine line at 100 nanometers. So that's pretty much Silterra can do. So down to ARF system. Okay. So I installed this system with my team back in 2000, I think about 2009, 2008 for the new technology. So this was the last one, and this is already very expensive. To acquire an EUV system, to purchase an EUV system, you need to spend a lot of money. Any guess on EUV price? Satu biji berapa? What do you think? Anyone would like to guess? Berapa harga an EUV system? 2 million, okay. Let's put it in USD, yeah. Okay, 2 million USD perhaps. 2 billion, okay, interesting. 10 to the 6, 10 to the 9. Ada lagi? Any other guesses? Sakina, 2 billion. Amirul, 2 million. Is actually in between, okay? So it depends on the details inside, but the current system that people are using, the top fabs, not simply people, is about 150 million per piece. If you talk about the recent version to enable 2 nanometer, 3 nanometer technology, it's probably around 300 million USD. Okay, per piece. Sebiji tadi tu je yang warna kuning gambar kan. And you need like 20, 30 of those in a production line. So just imagine that is the cost of the EUV system alone, not yet other equipments in lithography, not yet other equipments in other processes. So all in all, setting up a fab may cost you 20 billion, 30 billion at least now for the current technology. Right. So other than Silterra, what other wafer fabs do you know in Malaysia? Lagi fab lain kita ada kat Malaysia? You can unmute yourself. Osram, yes, Osram is also a wafer fab, but it's for solid state lighting, it's for LEDs, but it's a form of wafer fab. Yes, good, Arisha, on Semiconductor in Seremban, right? Seremban. Okay, any other? Fuji Electric, yes, Fuji Electric in Kulim High Tech. Infineon, yes, in Kulim High Tech as well. Lagi? Lagi? We have Mimos as well in KL. Mimos is also hosting a small area of wafer fab. Okay, untuk project-project government lah. Inari is not a wafer fab. We're going to explain later on. We're going to see later on. In electrical and electronics value chain, maksudnya dalam ekosistem EE tu, you have wafer fab in the front. You have design actually in the front. Yang awal-awal is buat design circuit. And then you send the design to the foundry, to the fab, to print the design on the chips. And then this is called front end altogether. And then we call another section as back end, where you dicing the chips, you potong chip tu. Yang tadi wafer 8 inch tu you potong. Jadi chip kan, every single chip tu. Then you package, jadi package yang ada kaki semua tu kan. Then you put it on PCB and blah blah, and masuk dalam products. So that's the whole value chain. You have front end and then back end. So you've answered this now. You've got Infineon, Fuji, Osram, on Semiconductor. Right. So TSMC, Taiwan Semiconductor Manufacturing Corporation, is the king of wafer fab in the world at the moment, right? So this is just a recent capture that I read on the internet about their plan on the 3 nanometer that will be released hopefully in Q1 2023. So that's like 2 years from now to get 3 nanometer technology in the market. And then the advanced version of 3 nanometer technology in 2024. And then we're going to have 2 nanometer technology in 2025. So it's going to be super exciting in the next few years. So if you look at this small legend, small capture here, you can see that the semiconductor market is dominated by Taiwan, right? So TSMC consists or dominates about 50+% already. And then we have another fab, UMC in Taiwan, so which controls about almost 10% or so. So altogether that makes 60 plus for Taiwan alone, right? So the dependency of the chip manufacturing worldwide is in Taiwan. So that's why kalau you ada baca berita baru ni, due to the pandemic, we have chip shortage kan? Ada baca tak? Chip shortage dan automotive tak boleh run sebab waiting for the chips and everything, right? Ada tengok berita tak? Ataupun you ada baca, right? You ada baca some articles ke? Kenapa tiba-tiba chip production halted ataupun slow down due to pandemic? Sebab kita punya dependency is mainly on Taiwan. Sebab Taiwan je ada all the state of the art technology. Yang lain-lain tu we have like global foundries in Singapore and US. We have Intel, we have Samsung and TSMC. So these are the top 4 fabs in the world, right? Intel, of course TSMC number 1, and then Samsung, Intel and GF, global foundries. So these are the 4 top fabs in the world. So ini je yang mampu buat. Even then within these top 4, Samsung and Intel and GF are lagging behind TSMC in terms of the technology capability. So the whole world is depending on Taiwan to get the chips to be out to the market. So that's why for manufacturing, for automotive, for consumer products, semua akan jadi slow down. Okay. So we have Samsung with about 20% or so market share, and then you have GF from US with about 7 or 8%, I believe, and we have GF in Singapore as well. Okay, so these are among the domination of the top wafer fabs. So back to this course. So just now it was a brief introduction to get you to the topic. So if you look at the course learning outcomes, by the end of this course, you should be able to look at the verb there. So we have 4 course learning outcomes. You're expected to analyze processes involved in fabrication of wafer and semiconductor devices. So analyze processes involved. You should be able to not only understand, but analyze, compare, see what's the difference, which process to use when, and why is it so, and stuff like that, right? So that's the first one. The second one, fabricate semiconductor devices on silicon wafer based on the fabrication processes. So if you look at the original plan of this course, we have a lab session for about 3 weeks, but due to the pandemic, I don't think it's gonna happen for this batch as well, because it didn't happen for the previous batch, because they were not allowed to be on campus, so therefore not allowed to be in the lab, and there's no physical activities on the fabrication. But it's actually a plan in the course where students need to spend about 3 weeks or so to do the fabrication in non-lab, and then get measure and characterize your samples to get some results, and then present the results in the form of group presentation. So we're going to see what is the progress for your batch, but one of the expected outcomes is the ability to do some hands-on fabrication. So the third one is to present semiconductor fabrication processes clearly with confidence. So you have done your presentation in 386 last time in the form of group presentation. So we're going to have that again, but instead of presenting on the device operation, you're going to present on the fabrication processes involved for a range of different devices. Okay, so remember that we're going to learn mainly about IC fabrication or transistor fabrication in this course, but we're going to cover the fabrication processes for some other devices during the presentation, where some groups are going to do fabrication of solar cells, for example, or SSD, so LEDs, for example. So you presented about the device operation in the last semester. So now you're going to need to present about the fabrication processes of those devices, okay, in the form of group as well. And the fourth one is you should be able to organize information related to fabrication processes, and these will be assess, especially during your assignments. Okay, so let's move on. So we're gonna have 14 weeks altogether for the course. So we're gonna have 18 weeks before the mid-sem break, and then we're gonna have mid-sem break in week 9, and then week 10 onwards is for the next 6 weeks of teaching and learning, right? So our classes will be on Monday and Friday, 2 weeks each. So we're gonna have Monday 10 to 12, scheduled for BT157, but it looks like it's gonna be on WebEx, just like usual, for 2 hours, and then we're gonna have another 2-hour session on Friday. So is everyone fine with this schedule? Do you have any other clashes? So the schedule works very fine for me for the time being. Is it okay? No issue, right? How many subjects are you taking this semester, by the way? Banyak ke? 4. Has it 4 ke? 4. Okay. Others? 4, including okay. 4 as well, 3, okay. 4 you have class. Monday 10 to 11 to 12. Okay, anybody else has a clash? Kali Monday 11 to 12. Seorang je. Kali, your class is for which course? Okay. Izati pun sama. Okay, Izati, are you on the same class with Kali for the 11 to 12? Or stat mechanics? Izati sama? Sama ke? Let me write down. Monday 11 to 12. Yang lain semua okay? Oh, Islamic studies, right? Let me write down first. Monday 11 to 12. Clash. So 2 orang je eh. How about others? Others semua okay eh? So let me see. When else can we do? Tuesday morning, do you have classes? Will everyone be free Tuesday morning? Say Tuesday. Hold on, I have Tuesday. Yeah, let me just unshare this. Confirm my. So. Hold on 1 minute. Tuesday, yeah. Tuesday morning, I'm good. Tuesday, 10 a.m. is it okay? Oh, you have a class. Oh, okay, you have a class 9 to 11. Let's see. How about Tuesday 11 to 12? Is it okay? Tapi 11 to 1 will you be free? 11 to 1? Kalau kita boleh ganti Monday to Tuesday one shot, 2 hours. It's a lot easier to do that if possible. 11 to 1, is everyone fine? Okay. Alright, looks positive. Ada yang tak boleh? 11. Okay, semua boleh nampaknya. Alright, so kita switch Monday. Monday 10 to 12. Jadi Tuesday 11 to 1. Right, so confirm Monday 10 to 12. swap to Tuesday 11 to 1. Let me go back to the slides. Okay, so so Monday, Tuesday is off. Friday, is it okay for everyone? Any clashes? 10 to 12 Friday? Sounds good? Friday can, slowly, yeah. Alright then, so Tuesday and Friday then. Tuesday and Friday kita mula next week, So esok tak ada kelas lah, Tuesday tak ada kelas lah. So next week kita akan mula Tuesday, Friday classes. Tuesday 11 to 1, Friday as original, 10 to 12. Okay, done. Nanti saya akan update accordingly on Elan with this slide. So Webex link macam biasa. So let's continue as usual. So let me give you a little brief on the assessment. Okay, so this course is going to be on 100% coursework again, right? So most of the courses decided to do 100% coursework based. So if you look at the 4 program outcomes that we've discussed in the previous slides, so the first one, the analysis part, analyze processes, is mainly addressing P01 in terms of program outcome, which is related to knowledge. P02 is intended for practical skills by doing the fabrication or hands-on work in the lab. CLO3 or course learning outcome 3 is associated with communication skills via your presentation. And then the fourth one is for a bit of digital skills. But I don't have any worries on you in terms of digital skills. You're all tech savvy, right? So, okay. So the coursework is 100% completely, right? No final exam. So we're going to have 2 tests, which accounts for 40% of your coursework marks. So each is going to contribute 20%, right, for the coursework marks. So we're going to have 1 test sometimes week 7 or 8, if I'm not mistaken. I'll come back to that. That will contribute 20%, and then we're going to have the second one after mid-sem break, perhaps week 14 or so. So that will be another 20%. So altogether 40%. So you're going to have 2 assignments as well. One is before mid-sem break, one is after mid-sem break, 15% each. So they're going to account for 30% altogether. Then 1 presentation in the second part of the course, right? On the fabrication processes on different semiconductor devices. So it's going to contribute about 30% of the mark. So 40 plus 30 plus 30, 100%. There's no final exam. So a little bit of course outline. So we're going to start with introduction to semiconductor fabrication, and then we're going to learn about the growth of silicon ingot. So we discussed a little bit about silicon ingot in 386, but we didn't really discuss on the process on how to do we actually fabricate the ingot, right? That's it. Yang macam bantal tu panjang sebelum kita potong wafer. So the growth, how do we actually do the growth of silicon? And then from the ingot, we're going to learn on how do we slice the wafers, prepare the wafers with acceptable specifications or specs before it starts the fabrication process. And then we're going to need to characterize the silicon wafers as well to see whether they are within the spec. Their spec, pernah dengar tak within the spec? Sebelum ni, we're going to learn later on. I'm going to teach you about a little bit about this. We call it statistical process control. It's going to help you for your interview later on. Process control. Kalau pergi mana-mana fab ataupun manufacturing, they will normally talk about SPC, statistical process control. So for example, if you want your line width to be 10 nanometer printed, okay, so you're going to have plus minus of acceptable variation. Okay, for example, so if 10 nanometer plus 0.2 perhaps, so that means if you characterize your line width, they can only fall within 9.8 nanometer kat bawah ni, and 10.2 up there. Because the spec, the limit is plus minus 0.2. So anything outside this region is considered out of spec. Okay, you only have to maintain your points, your measurement within this limit. Right? Semua kena duduk dalam ni, tak boleh keluar. The moment you're out, so your process, your equipment will be shut down. So nanti kita akan belajar the role of process engineer. I'm gonna share you a little bit equipment engineer, apa yang kena buat dalam wafer fab and stuff like that in order to sustain the process and the equipment. Well, all in all, it's called SPC. Okay. So characterization of silicon wafer, and then what is a clean room, bilik bersih. So how does it look like? What are the criteria for it to be a clean room? And then we're going to learn on the first process, which is thermal oxidation. Okay, how do we grow oxide? Okay, oxide, silicon dioxide on the silicon wafer. And then lithography, the printing of features by light. And then the etching process, the process that follows lithography, they normally run in pairs. You have to have your printing, and then you have to have your removal. Etching is removal, okay? Diffusion, in order for you to dope the junction, P or N type, or P plus or N plus. We've learned this last time in 386. And then implantation process, which is another form of incorporating dopants into your silicon by another method, ion bombardment. Film deposition, to deposit a very thin layer with various material. It can be dielectric, it can be metals. Okay, so then followed by process integration, where you have to oversee the whole processes involved in the fabrication of your device. And then interconnects and contacts. Okay, we need to print all the transistor. If you can recall, last time we learned about, if you talk about CMOS, and P, for example, if you talk about N type, so you're gonna have a channel here, you're gonna have your oxide here, and you have your polysilicon here, your gate, right? Gate. So nanti you're gonna have your you're gonna have to connect your features to respective contacts or metals. So this will be the interconnects involved. Okay, bila you dah siap buat main features, the active device, you're going to start to do your interconnect to connect to extract the currents and stuff like that. Okay, so then bonding and packaging, and then we're going to have a review class after that. Okay, we're almost done with the first part. Right, IC fabrication, we're going to cover from the growth of silicon ingot, and then once you have your ingot ready, we're going to see how do we then prepare silicon wafers from the ingot, right? Cutting, and then kita nak grinding dia, nak bagi sama, nak bagi smooth, nak bagi surface finish is the same, right? And then you go to the step 2 where you do all the fabrication processes. The oxidation, the lithography, the etching, the thin film, the implant, the diffusion, and many more things. Chemical, mechanical processing, RTP, and so on and so forth. So we'll be sitting in the middle spectrum here. So the first one is more on the preparation of the wafer, the ingot and the wafer. Then you do the fabrication here. So this is where your wafer fab lies. Okay. So normally kat sini wafer supplier lah. Yang first one ni wafer supplier ataupun ingot grower or wafer supplier yang akan buat lah industry kat sini. So wafer fab will be sitting here in the middle. Front end, we call it front end, FE, and then back end, BE. So you can see there, back end, front end. So if you talk about Silterra, Infineon, Fuji Electric, Mimos, onsemi, they are all here. Okay. If you talk about Inari, Spansion, AMDN. Then what else? All the backend companies, right? So they are all here. Jabil, Renaissance, they are all here. The backend. The moment chips are ready, okay, and package and then goes to the board and so on and so forth. Okay, so that's pretty much okay. Textbook. So I'll be using Jagger as the main one. I've given this details on eLearn already. So I'll be using this book, Jagger. Okay, ini buku yang saya beli back in 2002, 19 years old. Okay, so that's the first one. And the second one, I'm going to be using SMZ and Gary S. May and SMZ. I've given this on the I've given this on eLearn as well. The details, you can check it out, right? So these two books. So I'm using these two books as the main references. Okay. So as usual, just like what we had in 386, I'll be giving you YouTube videos, new articles and stuff like that, progress in the industry for you to read on and try to understand, to supplement your knowledge in the class. So I don't want to go through this responsibility because you are in your 4th year already. You are very well versed with all the procedures. Okay, no late submission of assignment, attendance, compulsory, plagiarism. You'll be scrutinized on your submission. Online attendance, you'll be based on the attendance will be based on the your presence here online. So I'll just extract your presence through the online class. Okay, you don't have to do any ticking on the system. So make sure you're present physically and mentally. Okay. So right. Okay. So why this course is important? Why do you think this course is important? Anyone would like to give your opinion before we finish the first part? Why do you think this course is important? Kenapa Juwariah and Sakina, you would like to join this course? You would like to share? Ju and Sakina? You boleh turn on your mics, okay? Or do you think this course is not that important? Future, okay? Again, any other thing? Can know how to fabricate the wafer, cost many things, use it. Okay, all right. Yep, straightforward. Any other things? Any other points? You can just add there, okay? So we already learned about the important concepts in semiconductor physics and devices in 386. And then in this course, you're going to learn about the fabrication, the processes, okay? So that will complement your previous knowledge. So bila you belajar the device physics and you stop there, for example, it will not be enough because you know how the devices work, but you don't know how to fabricate the devices. On the other hand, bila you belajar 386 plus 487, you know how the devices work, and then you learn how to fabricate the devices. Okay, your knowledge will be complete. Okay, baru-baru ni, if I can share, I just had a meeting with GF Singapore last week. I got a message from the senior director of process integration to look for our students, USM student, in particular applied physics. Not to say that others tak boleh, in particular applied physics and engineering schools. Okay, so because for applied physics, to be more specific, because you learn this course, you learn about the physics and devices, and then you learn on the fabrication. And for your information, if you have a plan to work overseas, for example, kalau nak kerja Singapore, GF Singapore is now expanding, and they are investing about 4 billion USD for the next 3-4 years to expand the wafer fab in Singapore. And we just had a meeting last week with the talent acquisition team looking for USM student. And I've roped in hebat punya team daripada USM. Apa tu? HDC kan, Hebat Development Center, to arrange for a career talk by GF later. So I believe it's going to be soon, but it's not yet determined. But they're going to arrange a career talk with all the USM students, and they are looking forward for your submission to join them if you want to work in Singapore. Especially kalau orang duduk selatan dan Johor ke nak kerja kat Singapore, then it's a good time for you, right? So GF is looking for us, USM. So that means we are doing good, right? So that's a very strong testimony from one of the top fabs in the world, GF. Give hands-on skill on semiconductor fabrication processes, and then you're going to learn on the vital foundation to enter industry in terms of the processing on top of your device physics knowledge. So whatever that you learn in this course is going to be applicable for some other industries as well, like solar cells, LEDs, SSDs. So we have plenty of different industries in Penang alone, right? If you look at Penang, Batu Kawan, Island, Prai, Kulim High Tech, we have plenty of different industries, different companies, MNCs, locals that you want to choose if you want to, right? So we are in a way we are actually blessed. We are blessed. Kita apa ni? Nikmat lah, antara nikmat yang kita ada ialah kita blessed with to be in the neighborhood of industry zone, especially semiconductor, okay, especially electrical electronics. But EE accounts for about 38 to 40% of our national export, right? Recently, it's about, I think, about 40% of our export is from EE. So maksudnya the region, our region is very strong in terms of EE and semiconductors and so on. So a brief of EE sectors. Monday, apa yang tujuan? Okay, but Monday 10 to 11, Tuesday 11 12. Oh, you have another clash. Monday 10 to 11, Tuesday 12 to 1. Okay, so if that's the case, I have to break into 2 classes then. Hold on. Ini you punya minor ke? So if possible, I'll try to combine into 2 hours straight. Minor daripada sekolah lain lah Okay. I'll try to, because I would like to combine them 2 hours one shot if possible. Unless we have some other time. Nanti kita discuss offline lah, Juara. So for now, let's just stick to that first. Okay, so EE subsectors in Malaysia, we have 5 altogether. So when we talk about electrical electronics, we have a very big domain there. So in EE subsectors, we have 5 altogether. So we have semiconductor, one of them. We have optoelectronic and LED is the second one. We have solar PV, the third one. We have system electronics, the fourth one, and we have manufacturing related services. So if you want to say work or go and do your intern in this EE, one of these EE subsectors, you'll probably land a post, internship post, or your career in one of these subsectors. Okay. So if you look at the spectrum down here, EE value chain in Malaysia, as what I've told you a few minutes back, we have IC design on the front end, where we design the circuit, and then we go to the foundry to fabricate the circuit, right? The first one is here. Oops. Hold on. Okay, the first one is IC design. Okay, the first one is IC design. And then once the design is done, is fixed, then you have foundry. Okay, you have foundry. And then the moment the fabrication is completed, we send the chips to assembly and test, and then to the backend. Okay, so this is how all these 5 subsectors are late in terms of EE value chain, right? Electrical electronics value chain. So you know that we are in the neighborhood. So Malaysia is strategic hub for semiconductor manufacturing. You can see by the total export of about 40% is from EE domain. So Kulim and Penang are the nearest example. We have solar industry, we have some other industry as well. So if you're not into job market and you would like to continue your postgrad, for example, at MSc or PhD level, then our school is working on few R&Ds on different semiconductor devices as well. Materials and devices like LEDs, solar cells, transistors, detectors, sensors, and many others. So yeah, before I finish the first slot, what is your plan after graduation? Have you got any plan at the moment already? Have you got anything crossing your mind so far? Or you already have something specific to go for, or tak ada idea lagi? You can be open with me, it's okay. It's okay not to have a plan yet. No worries. No plan, okay? That's okay. How about others? Has anyone got a plan already? Nak kerja luar negara? Okay, boleh, tak ada masalah. No worries. Where do you want to go? You have to have a strong foundation for you to go outside. So perhaps a GF is the first starting point, since they are now looking for us if you want to. Okay. Singapore. Yeah, Singapore is quite interesting if you want to go there. Okay, any other plans that you can share with me? Is okay. Mungkin most of you tak ada apa-apa plan lagi kot. Is it correct for me to say so? You don't have any inclination yet, perhaps. Kerja dan beli rumah. So kerja kat mana tu? Well, you can start do the thinking from now. It's okay. Because your next semester is going to be on internship. If you want to go for internship, it's not compulsory though, but it's highly encouraged. So most of the students who manage to get a placement are usually absorbed if vacancies are available in the companies, and if you perform. Don't know you can okay, so it's all right. Okay, so we are done with the first session. Do you have any questions on the first session? We're going to go for a break for like 5 minutes, and then we're going to come back for the first topic. Do you have any questions on the anything, assessment on the course itself before we start officially with the first topic? Boleh cari kerja macam Huawei? Yeah, of course you can. So as long as you have you fulfill the requirement, then it should be okay for you to try. And for your information, Infineon Kulim pun sekarang tengah expand dia punya operation. If you read the latest news, they are going to bring silicon carbide and gallium nitride epitaxy to Malaysia soon. Okay, based on minister discussion lah. So they're gonna bring that. So then it's going to open for more job opportunities in Infineon Kulim. Front end, bukan back end, front end. And even now, few weeks back also, saya punya kawan dekat Infineon asking for new students to join Infineon under dia punya team and some other team as well. So they are doing quite hiring at the moment. So if you fulfill the requirement, especially on device physics, on the fabrication, then you should be eligible to try. So those are some of the good news, because industry is expanding quite a lot right now. Right, any other question on the course introduction? Is everything clear from the introduction? Okay, Right, if there's no other question, then let's just don't leave the session. Let's just have a break of about 5 minutes. Sekarang berapa? Sekarang 11:05, then we'll continue 11:10, okay? So have 5 minutes break, nak pergi toilet ke, nak minum ke, whatever. Have your breakfast ke for 5 minutes. Go ahead. I'll turn on my camera and start the course at 11:10, okay? See you in 5 minutes then. All right, let's continue. Let me share the slides for the first topic. Okay, can you see the slides? All right, good. So let's get started with our first topic, introduction to semiconductor fabrication. Okay, so what makes integrated circuit? So what do you think is the material that we use to make the ICs? Anyone? What do we use? What is the core material there? Yang dia tengah pegang tu. Silicon. Okay. So she's holding, I think she's right. She's holding a wafer or two wafers made of silicon, and silicon is made of sand, right? Made from sand. So you're gonna see transistors and many other devices as well. So can you guess what is the diameter of the wafer on the left? Yang kecil tu. What do you think is the diameter of the wafer? Any guess? In terms of inch, berapa inch rasa-rasa? Ataupun in terms of mm? We normally use inch and mm in wafer fab. 25 cm, okay. Ready, 25 cm. Any other guesses? 1 inch? 4 inch? Diameter, diameter, hujung ke hujung. Berapa inci? Any other guesses? 4 inch. Yang kecil ya, small, yang the left hand side. Any other guesses? 4 inch. Okay, lagi. Anything? Would you like to go bigger? Anyone? Aziz, dengan ukur tu sama apa Aziz? Imagining in the air, 10 inch. Okay, I middle 10 inch. Agak-agak lah tengok dimension tangan dia, kepala dia, badan dia, more or less. It's 12 inch, okay? 12 inch. 12 inch is 300 mm. So normally kita pakai dekat Siltera we have 8 inch. We're using 8 inch. 8 inch, so that's about 200 mm or 20 cm in diameter, which is smaller than this. And this is like 12 inch, a more advanced version, 300 mm. Okay, so now let's guess what's the diameter on the right. Wafer on the right. Kalau kiri tu 12 inch, agak-agak yang kanan tu berapa inch? By the relative size. So Haziq, what's your result from the air measurement now? 20 inch. Okay, Haziq, 20, 24, 24. Okay, 25. Right, so you're going double. Okay, any other? Anyone would like to go bigger or smaller? 15, Fakri, 15, okay. 17, okay, Arisha, 17. Any other guesses? Sebelum itu continue. So that's about, the answer is, paling dekat dengan Arisha, 18 inch. Okay, 18 inch, Arisha. Dekat je dengan yours. It's about 450 mm. So that's the biggest that we have at the moment. So right. So 18-inch. So if you use 10-inch, well, we also have in the industry right now where some companies are using 4-inch and some are using 6-inch, and Silterra is using 8. I think Infino is using 6, if I'm not mistaken. And we don't have anything 12-inch in Malaysia because the biggest is 8-inch. We have some other fabs doing 12-inch, some other exploring 18-inch as well. The 18 is very big. So when you go bigger, so the pot, nanti kita akan tengok pot yang holding the wafer. One pot normally holds about 25 wafers. Satu pot tu dia ada macam slot untuk isi every wafer. We're going to see later on. Each pot accommodates about 25 wafers. So the bigger the wafers, the bigger the pots get and heavier the pot gets, right? Or some of the logistics in the fab are done by the operators where they have to bring, they kena carry the pot, carry bawa. Kalau lagi berat lagi ada isu lah dengan isu untuk handle the pots and everything untuk kesihatan. But most of the processes are done by automation. Okay, nanti kita akan explore, automation will handle pretty much everything in the fab. Only some processes are handled manually. So that's 12 and 18-inch. Right. Integrated circuits are made of silicon. At least the one that we are using right now is based on silicon, and silicon originates from sand, and the sand is a silicon dioxide, right? SiO2, and the SiO2 that we have as the precursor material is reduced by removing oxygen to make it a silicon, and then the silicon is purified a couple of times using high energy processes. We're going to learn it on high energy processes to purify the silicon to certain purity level in order for it to be used in semiconductor industry. So it's not like just removing oxygen and you get silicon and that's it. So you have to remove the oxygen, leave silicon, purify the silicon to certain purity level, then only it can be used as a transistor. Okay, so, and if you talk about devices based on silicon, different devices require different levels of purity. Okay, for example, if you talk about transistors, a transistor need about 9N purity level. 9N purity level. So let me just write it down here. So we're going to come back to this eventually, but just put it down. So if you talk about transistor, you're going to need to use 9N. So that means you're going to need to have 99 point, another 7 of 9s. 99.9999999%. So which is 9N for transistor. For solar cell, on the other hand, you only need 6N. Okay, 6N solar cell, 9N transistor. Maksudnya dia kena very pure, silicon kena very pure for it to work as a transistor. So you have to have 9 kali 9, 99.7, 9999999%. On the other hand, if you want to fabricate solar cells based on silicon, you only need to have at least 9N for it to operate properly. So that means you need to have 99.9999% in order for it to work properly as a solar cell. But kalau you ada 6N, but you're gonna make it work, you want it to push it to work as a transistor, it simply won't work because it requires 9N of purity level of silicon for it to work. Okay, so silicon chunks are processed to become bare silicon. First one, you use this sand. Kalau pergi batu ferigi ambil sand, for example. Okay, and then we're gonna have to go through some processes. We're gonna get to that later on, which is going to convert silicon dioxide into silicon chunks. So this is the silicon chunk macam batu ya. So these are the chunks, right? So then we're gonna melt the chunk in a process that we call a Czochralski process. They can melt the chunks kemudian kita akan grow dalam grower. We're going to cover that soon. Then you're going to end up with ingot. Okay, ingot. This silicon is the wafer as a result of the ingot. So ingot is pretty much like that. The vertical part macam bantal peluk. So then you're going to slice that portion into hundreds or perhaps thousands of wafers, depending on the thickness. Okay. Right. If you talk about semiconductor materials, so germanium was one of the first few materials used in semiconductor device in Bell Lab back in 1947. The first one used in Bell Lab in 1947. That was like years ago, and it was then replaced by silicon in the 60s. Okay. So why silicon? Silicon can be oxidized easily for high quality SL2. We're going to learn this in oxidation later on, where we form a thermal oxide or thermal silicon dioxide in order for us to use it as effective barrier in diffusion process and also in isolation process. Electrical isolation, that's why SiO2 is an insulator, okay, not a conductor. So why silicon? Silicon has higher band gap compared to germanium. Germanium has 0.7, right? 0.7, silicon has 1.12. Therefore, we can operate silicon at higher temperature relative to germanium. Okay, remember last time we talked about the band gap and everything, right? The thermal excitation, the energy required, and all those stuff in order to thermally excite our valence band electrons from the valence band to conduction band. So the energy required will be more and more as the band gap increases. So therefore, if you compare silicon to germanium, 1.12 versus 0.7, of course, silicon can handle high temperature. But if you compare silicon to some other materials, perhaps wide bandgap semiconductor materials with 2.0 EV or higher, and of course, those materials can stand higher temperature. Silicon is an abundant element in nature in terms of sand or SL2, and therefore inexpensive for us to use, right? The economic aspect of the semiconductor material for manufacturing. So beside germanium, we have gallium arsenide, right? So gallium arsenide, if you can recall last time we talked about the mobility of gallium arsenide. Kita ada discuss tentang mobility versus doping level curve kan? If you can recall, mobility of electron in the hole versus doping level Na and D in 386. You can see the curve and stuff like that. But if you compare the mu E for gallium arsenide is way higher than mu E of silicon, right? So that's why, due to this, gallium arsenide is usually used in high-speed transistors. Okay, so why the mu E is a lot higher than mu E of silicon. So high-speed circuit in excess of 1 gigahertz, even though you can push the capability of silicon, but by the intrinsic properties, germanium has higher mu E compared to silicon. So this is a bit of history of the first semiconductor materials, the first transistor invented in Bell Lab. You can read through the article later on in 1947, okay, by Shockley, Bardeen, and Brattain. Shockley ni tiga orang, Bardeen and Brattain. So they are the one who discovered the transistor in Bell Lab back in 1947. So if you look at the shape of the transistor, so this is how it looked like back in 1947, right? It's a form of bipolar junction transistor. We learned this in 386 BJT. So this is a very simplistic form of BJT, right? There's nowhere near to what we have today, right? But this is how it started back in 1947. Then the first integrated circuit was invented in 1958. So integrated circuit means you have more than one discrete device on a circuit, right? You had a multi combination of different devices on the same circuit. So that's why we call it integrated circuit or IC. So in 1958, realized by Jack Kilby from Texas Instruments, a device having multiple electrical components. So that's the key. IC means multiple electrical components and their interconnects on a single substrate. So that's why bila kita sebut IC tu, integrated circuit. So that means multiple electrical component on a single circuit, on a single substrate. Okay, and that's how it looked like back in 1958. The first one, the first version of IC by Texas Instrument. Okay, so this is the details. You have resistors, capacitors, transistors. You can look at the invention there back in 1958. And then let's go through the evolution of microprocessor by Intel. If you look at 1971, in this space, it was only like 2,300 transistors. Speed 0.108 kilohertz here, operation ya. Pakai PMOS 10 micron process. So if you can recall PMOS, ya tak PMOS, what is the difference between PMOS and NMOS? Anyone? Apa beza dia PMOS and NMOS from the previous course? How do you spot whether it's a PMOS or NMOS? P or N? Kat mana nak tengok? If you have a MOSFET, for example. How do you tell? Anyone? From 36? Ramai dapat A kan? Tak? Zik? How do you spot? Where do you tell? Gate, oxide, say this is N and P. So, okay, Faris cakap apa tu? Faris, source and drain, N-type, NMOS, vice versa. Source and drain. So that's determined by, well, what do you call that? What do you call that area physically? Oh, sorry. What do you call this area physically? This is, you said source and drain. Yeah, what do you call this area physically? The shaded area. It's determined by the, what's the word? Anyone? You're close. Faris, source and drain, N-type, NMOS. Yes, in this case, it's N-type. Source connecting source and drain. But what is connecting source and drain? Apa nama dia? Lupa lah. Anyone? Here ke get outside? Are you sure? Get outside is up here. There, get outside there. Under the gate. Gate kat atas. Gate aux bawah gate. What is connecting N and N here? Source and drain. What's the name here? Anyone? Come on. Depletion layer? Not quite. Come on. Let's recall 36, guys. 2 months ago. What's the word there? What's the most important word to determine whether it's PMOS or NMOS? Starting with C. Come on, anyone? Apa perkataan tu? There you go, Arisha. Good. Channel. Tak lupa lah channel. Channel, okay, that's the word. Connecting source and drain. Channel. So the PMOS, whether it's PMOS or NMOS, is determined by the channel. Okay? Good, Arisha. So if your channel, the connector bridge tu antara source and drain tu kalau N and N, so N channel, right? So in this case, in this drawing, it's N channel, and the substrate or the wafer is P type, so the channel is N connecting N and N, so N type. So we call this NMOS. In this drawing, it's called NMOS. Tapi dalam nota ni, in this lecture note, it's about PMOS, right? So it has to be the reverse version of this. Okay, so for 108 kilohertz of operation, the speed, the frequency, the technology back then was only PMOS with 10 micron process. So that means if you talk about the micron process, you can see the gate size is pretty much 10 micron. The width of the gate width, 10 micron, very, very, very big. If you compare to the previous slides, just now we covered in the first part, we're talking about 7 nanometer. We're talking about 5, 3, 2 nanometer. And this is about 10 micron, right? 1000, 10,000 bigger than the current version. Okay, so capable of 108 kilohertz of operation. So in 2000, tadi 1971, then in 2000, so we started to have 42 million transistors, 2 gig of operation. So 0.18 micron. So sama, maksudnya dia punya gate width ni is about 0.18 micron. Ataupun if you change this to nanometer, so that's about 180 nanometer. So this is the gate and everything else. Okay, so capable of 2 gig of operation, early 2000. 2008 Intel Core 2 Quad, right? 2008 with 820 million of transistors, 2.83 gigahertz of operation with 45 nanometer of gate width. Gate width ni kalau dalam bahasa fabrication, we call it CD as well. Critical dimension. Remember the YouTube video tadi kita tengok ni? Right? The width is about that. Okay? So 45 nanometer back in 2008. So what's the current speed of laptop that we have at the moment? Anyone has seen, what's the maximum? Anyone? You follow the development of the processor? What is the highest that we have at the moment? 3 something? Do we have 4 gigahertz at the moment? Abang, di research try tengok 4 gigahertz and try to search berapa dia punya gate size atau technology node. Technology node, and we also call it technology node. This is the language that people use in the fab. Technology node, or some even call it process technology. So in different articles, you may encounter technology node or process technology, but it's actually referring to the very same thing. This one. Cuma dia pakai different languages or different words. Okay, this is the same thing we discussed just now in the first part. So today's ICs contain billions of transistors. Okay, so we're going to learn in this course how do we convert from SAN to bare wafer to integrated circuits through various fabrication processes. So if you talk about a wafer fab, normally, if you talk about a fab, normally wafer fab it will receive bare wafer kosong, silicon bulat. There is no circuit at all. There tak ada circuit ni, tak ada lagi, kosong. Plain shiny silicon wafer, kosong. So itu input to wafer fab. Sebelum tu supplier akan buat all the ingot growth and the slicing and measuring the spec and everything. And then, for example, a wafer fab like Silterra, it will receive wafers from wafer supplier, and then in the form of bare silicon wafer, and then it will convert the bare silicon wafer into all this with integrated circuit eventually. So the process typically takes about 2 to 3 months. So maksudnya masuk hari ni lagi 3 bulan baru keluar and complete IC. And then this wafer with the ICs on will be sent to back end for dicing. Dia akan potong, itu Silterra tak buat dicing. Company lain akan buat all the dicing and then package the chip and then put on PCB. Semua tu back end punya company akan buat. Silterra tak buat. Front end lain pun tak buat. Right? So because running a fab is already super expensive. You tak mampu nak buat all the back end, front end together because it's simply too expensive. Right. When you talk about evolution of ICs or circuits or transistors, there's a law that we call Moore's law. It's not a law like typical physics law, but it's more of an observation. It's actually an observation. It's not really a law. Okay, lebih kepada pemerhatian dia, but it's later called a law, more or less. Right, Moore's law refers to an observation made by Intel co-founder Gordon Moore back in 1965. Right, his observation was he noticed that the number of transistors per square inch on ICs had doubled every 2 years since their invention. Every 2 years, the number of transistors will double. 2 years double, 2 years double. So that's what he observed since 1965, right? And furthermore, also predicted that this trend will continue into the future. Sampai sekarang, walaupun sekarang kita dah sampai ke limit lah, we're talking about 5 nanometer, 3 nanometer, 2 nanometer, and then what else? What else is beyond 2 nanometer? Sebab nanti kita akan approach the silicon atom size kan eventually. And then the system that we need to be able to do all the printing and fabrication simply gets more and more expensive because you need to do more and more things with great precision, with great resolution. So simply gets more expensive. So that's why a single EUV equipment with high-end capability targeted for 3 nanometer, 2 nanometer is costing about 300 million USD each for one piece. So simply gets too expensive. So smaller transistors simply mean faster, right? Faster switching. You can fit more transistors onto the same area. So that means for the same area of wafer, 8 inch or 12 or 18, certainly you can pack more and more transistors onto the same area. And it will consume less electricity as well, right? So this is pretty much what we discussed all this while, including in the previous course. So we're talking about the gate length, the poly gate length here. And then you have gate ox or gate oxide below. And then you have a source and drain on the left and on the right. And then the bridge connecting source and drain is called channel. This is what we'll discuss now. Below the oxide, and then you have the substrate. So this is the starting wafer that we are using in the fab. And then we're going to fabricate all these structures onto the bare wafer. Sampai habis lah. Then this will be called the front end part. And the moment the front end structures are fabricated, we're going to see interconnects will be fabricated later on to get to the final chip. Okay, nanti kita akan tengok throughout the course. Okay. So this is Gordon Moore, and you can certainly go and read the PDF of the paper. So the number of transistors and resistors on a chip double every 24 years. So yep, holding the wafer, Gordon Moore. So you can see here number of transistors on the y-axis against a year of introduction on the x-axis up to 2016. So here, if you look at 1970s, we only had about 2,000 or so number of transistors. And then in 2016, it's already up to this point, okay? 10 billion, 10 billion transistors, okay, in 2016. So from 10 to the 3 to 10 to the 9, okay? So that's the orders of magnitude change in the span of about 30, 40 plus years, 40, 50 years, okay? So number of transistors in the table. So you can see 2003 back in 1971 up to 2008 is already up to 820 million. So it's now billions already. A clock speed. So ITRS is the roadmap that governs the development of the field. Okay, International Technology Roadmap for Semiconductors. Kalau dalam solar cell, we have ITRPV, ya. International Technology Roadmap for PV. ITRPV. So kalau ni ITRS, Semiconductor ITRS. So this is the roadmap lah untuk what to outline what are we supposed to achieve in the next few years. So it's actually driving the industry to be more advanced. Okay. So wafer size over time. So back in 1975, it was only like 100 mm or 10 cm. Okay. Then it grew over time up to now 18 inch. Okay, this 18 inch is the biggest one. 12 inch, 8 inch. Okay. So if you want to upgrade the fab into, if you want to shift from 8 inch, for example, to 18 inch, it's going to be very costly because you're going to need to have a new fab. Sebab equipment yang you ada untuk run 8 inch only can fit 8 inch. Chamber dia boleh fit 8 inch punya wafer ya. It will just be just nice in terms of size. Robot arm and everything will just be holding 8-inch wafer. It's not capable of doing automation for 12-inch, for 18-inch, right? So that means to be able to switch from 8-inch to 8 to 12-inch even, or 12-inch to 18-inch, or 8-inch to 18-inch, you simply need a new fab with 18-inch of capability in terms of the equipment size and robot arms and everything else, right? The port system to hold the wafers throughout the processes. So by that, it means if you want to establish, or if you want to build a fab with 18-inch capability, it will be simply more expensive if you compare to 8-inch fab. Okay, so it's not simply like upgrading to new equipment. You simply need to change the whole equipment in the production line to accommodate your new wafer size. So back in 2017, IBM with 5-nanometer chips. Okay, you can read here for desktop PC and laptops with typically 14 nanometer and 10 nanometer. Okay, building. Okay, back then it was. Today back in 2017, IBM announced first industry first process for 5-nanometer. It's already demonstrated by IBM about 3 to 4 years ago. And you can go check out the article here in terms of the invention. Right, this is the EUV for 5-nanometer chips. So so that is the size that it takes for a single EUV, and you're gonna need like 20 plus at least for a single production line for EUV in lithography alone, right? So this is the cross section inside. So you're gonna see later on, you're gonna need to use EUV light source with exposure stage, with a measurement. There are thousands of different stuff inside this scanner. We call this scanner scanner. So this piece costs about 150 to 300 million per piece, per piece USD, depending on certain features inside, right? So the recent version is like 320 million per piece. Right, TSMC 7-nanometer chips. You can see the fab facility for 7-nanometer established in 2020, last year. So this is some summary of future R&D plans by TSMC. You can see here in 2021, they're planning to fabricate 3-nanometer logic technology platform using 3D CMOS architecture. Okay, so kita dah belajar in the last course about FinFET and everything, right? So this is among the technologies that will be fabricated or will be used to realize the low technology node. Okay, 3D IC 2018, 2021, next generation lithography to extend Moore's law, and also long-term research. You can see all the stuff planned for up to 2026. So let's go for another 5 minutes. So Moore's law will not stay forever. Why? Because at some point it will reach the fundamental limit, and the fundamental limit will be the size of the semiconductor that we use in the chip, which is silicon. And even before talking about the fundamental size of the silicon, it's already difficult to realize a high-tech exposure system to get your features printed with good resolution. So tu tak sampai dekat bab fundamental size lagi. It's already complicated at this point. 7-nanometer, 5-nanometer, 3-nanometer, going for 2-nanometer. It's already complicated enough, right? So, but eventually it will hit the wall. And in terms of the size, it's no longer capable, and we're gonna need a new technology to be in the equation, right? Approaching the size of atoms, which is a fundamental barrier, but it will take about 2 or 3 generations before we get that far. So in terms of the capability of the equipment, is already difficult to realize. So you can go and read this article about the 50 years anniversary or 50 years achievement of Moore's law. What have you got up to this point? what has been overcome and what is there still to overcome in the next few years, right? So value chain, the focus will be here in for wafer fab right after the design. So we're going to learn later on when you want to print your circuit, you have to have your circuit design first. Okay, so circuit design is will come in the form of a mask. Okay, macam you nak print baju tu, you kena ada dia punya mold kan, dia punya features kan yang you nak print tu. So in this context, for lithography, we're going to need a mask. To print, dia akan mask ni, it will outline all the circuits that you want to print exactly on the wafer. And this mask is called reticle. We'll encounter this again in lithography process later on, but just brief for you. So then the reticle, the mask, the features on this mask will need to be smaller and smaller and smaller to get down to the intended size. Okay. So in this course, we're going to learn on how do we get the polysilicon chunks from the sand, how do we do the conversion, and then how do we then melt the polysilicon chunk and grow the silicon ingot, and then how do we then slice the ingot to get to wafers, then use the wafers and do all the fabrication processes. This is pretty much what we're going to learn next in the next class. So polysilicon chunks melted into liquid silicon. Okay, anyone knows the melting point of silicon? You have to melt the polysilicon chunk. So maksudnya you have to overcome the melting point, right? Anyone knows the melting point of silicon? What temperature can melt silicon? You can Google now. Tengok apa temperature dah. Because you need to melt the silicon eventually, so you have to overcome that temperature to be able to produce liquid silicon. Okay, you can write down in the chat box if you found it. Anyone? What's the temperature that needed to be overcome? Yeah, 1400 degrees, right? Okay, thank you. 1400 degrees. So that means the process, this process has to be done, has to be carried out at above 1400 degrees C. Okay, above 104 degrees C in order for us to melt the silicon. Okay, so you need to produce liquid silicon. Now melt dulu, then only you solidify to form the ingot. Nanti kita akan belajar next process. Kita akan belajar in the next process how do we convert first sand to polysilicon chunks, part 1, and then part 2, how do we then use the polysilicon chunks and then produce silicon ingot before we slice the ingot into wafers. Okay, so this is the ready ingot on the right, and then the ready wafers on the right as well, the moment the wafers have been sliced from the ingot. So there are a few key processes in this fabrication. So the moment you've got your wafers sliced from the ingot, fulfilling all the criteria, all the process specifications for fabrication processes, then we're going to have this wafer ready. Okay, wafer will be ready. And then briefly, we're going to grow a very thin layer of oxide on the wafer. Remember kalau you buat CMOS tadi, kita schematic, you have gate, polysilicon gate, and then you have gate ox below the gate, and then you have the substrate, right? Where you have your source on the left, drain on the right, and then you induce the channel formation when you apply the gate voltage. So this oxide will serve as the gate ox. Okay, kalau you draw full structure, it's going to be something like that. Okay, you're going to have gate here, and then eventually you're going to have source and drain kat sini, tapi we're going to do something else after that in order for us to get to that structure. But this oxide for this particular step is for gate ox, right? Gate oxide, bawah gate. Then you apply a photoresist. Photoresist is a sensitive polymer compound. It's a compound that we spin coat. Kita spin coat dia. Kita cover this green area. Kita titik dia. You dispense a few ml depending on the technology, and then we spin to cover the whole surface, and then the surface will be covered with a light sensitive polymer compound, right? Which will act upon exposure to the illumination light later on in the scanner. Okay, and then you're going to use your mask. So this hitam putih ni actually is your mask, which will allow the light to pass through certain area. In this case, the central part will be allowed to pass through, and then this area will be blocked. Ni hitam ni dia akan block light lah. So maknanya light kita akan expose daripada scanner nanti. Kita akan sampai ke situ. But the black part will block the light from being transmitted through the mask. Okay. Then you end up only this area is effectively exposed to the light. This central part je. Sorry. Jangan, kenapa dia block pula? Okay. Dia tukar slide pula. Hold on. Jangan, just one slide to finish. Okay, nampak kan slide? Just to confirm. Okay. Can you see? Okay, good. So, this green part, the central part, green kat tengah ni je yang akan expose. Okay. The exposed area will have some reaction. Okay, dia akan induce reaction depending on the resist type. Kita akan cover later on, but that's the key. It will induce a reaction. Okay. So, tengok kat sini bila dia expose. So, exposure dia akan expose dekat tengah je, sama yang saya draw tadi. Then, the exposed area in this case will be dissolved. Bila dia dissolve, maknanya dia punya structure tu kita akan buang lah. Kita akan buang, so eventually you're going to be left with this. So this will be removed, this area will be removed, this area will be maintained. Don't worry yet. We're going to come to lithography later on to explain this further. So you ada structure kat sini. So mula-mula you code semua, then you define pattern. This called patterning. Bila you ada buka certain area, cover certain area is called patterning. So maknanya in terms of circuitry, later on you're going to have circuit at some point in some areas and no circuit in some other areas. So it's called patterning. Kita patternkan dia. And then the moment it's open, is exposed, you can actually do the doping process. You can expose. So area ni dah tak di cover oleh mask, oleh resist. So you can then send your dopant such as boron or phosphorus or whatever into this exposed area to do the doping for P-type, N-type, P+, N+, P++, depending on the design. Okay, so that's the key things that we're gonna cover in this course. Okay, so nanti kita akan go through the next one to convert the sand into polysilicon chunk, and then polysilicon chunk into wafers, and then prepare the wafers, and then go through all of these processes from oxidation, photolithography, etching, diffusion, implant, thin film deposition, sampailah kita punya IC tu complete. Sampai you ada metal line lah untuk measure bond pad and everything. You can see the final version of the chip, right? So this is essentially what we're going to do. We're going to cover in this course. Right, so we're down to the second part of the 2-hour class for today. Any question from the second part that you don't understand? You like to ask anything?
Doktor.
Okay.
Saya tak ada soalan, tapi tak ada soalan berkaitan dengan apa yang doktor ajar, tapi nak tanya pasal apa tu, kan untuk IC design, software apa yang biasa digunakan?
Software dia multiple lah, dia ada banyak version. Selalunya yang belajar ni student EE lah. I think if I'm not mistaken, I think they use Cadence. If I'm not mistaken.
Cadence.
Cadence, C-A-D-E-N-C-E. I believe there are a few more platforms that they use to do the design. And industry pun mungkin ada multiple platforms juga to do the design. So if you talk about the design, then it's mainly design the circuit. Dia tak ada duduk dalam fab. design ni usually we do it in the design house. Macam if you have heard of Altera, for example, I think dia dah bought over by Intel kot. Dekat Penang, dia design house. Dia main IC designer ni, dia just duduk kat depan PC je dia punya kerja dia. Ataupun laptop and just design the circuit. So you define area mana ada circuitry, area mana tak, the width, the size, depending on the current requirement untuk you extract atau inject current later on. So purely the design. Then the design house punya output will be the design of the circuit. Then will be transferred onto mask ataupun reticle. So dia ada dia punya own supplier jugalah, vendor yang supply the reticle, and then reticle tu will be used, will be purchased by the wafer fab and used to do the printing. Macam kalau kita nak print baju, kita kena ada kita punya tulisan tu kan. So that's essentially the thing that you need to print the circuitry dalam bentuk reticle lah. So tapi bahasa mudahnya is the printing of the shirt lah. Just imagine the writing on the shirt is as the circuit that you want to print down with certain size and shape and everything. So yeah. So design house is usually independent dan IC designer lah yang design. So they don't necessarily have to know fabrication processes in order to do the design. But it's always good to know. They only have to know the design requirement with whatever platform that they use. Intel pun ada buat kat sini. Intel ada design engineers yang design all the circuitries. Cumanya, I think for Intel, for example, they do the design here and perhaps some other parts of the world as well. And then the design will be transferred to the wafer fabs somewhere else, perhaps in the US code into Intel. And they do the fabs there. And then the backend will be coming back here in some other location worldwide to do the backend. And then you complete the whole product. Okay. Any other questions? Anyone else? Okay, we change the time. Okay, let me see. Tuesday tadi you suggest berapa? Anyone else has a class Tuesday? I forgot the times now. Monday 10, 11, Tuesday 10, 12. Right. Anyone else has a class Tuesday 11 to 12? Ada ke? If you want to do the second class Tuesday 11 to 12, then we're going to have 3 days with our classes. Semua tak ada clash. If not, then maybe we can do Tuesday as well as the second part. So if that's the case, then we need to have a class on Monday 10 to 11. Then Tuesday 11, hold on, let me see. Tuesday 11 to 12. Tuesday is, I think it should be okay for me. Oh, you have a class. 12 to 1. 12 to 1 Tuesday ke? Is there any? Oh, you have a class 12 to 1. Hold on. If 11 to 12, is it okay? Oh, but then Monday tadi 10 to 11, any clash? 11 to 12, okay. Nanti kita discuss dalam ni lah, WhatsApp lah. WhatsApp group lah. Kita discuss on the time. But at least for this week, let's continue as usual. It's going to start next week anyway. So nanti kita discuss dalam WhatsApp group lah, tengok macam mana how to fit in. Right, any other question? Oh, 12 already. Ada? All right, then, if no question, then I'll see you on Friday, right, for our second class. Okay. So in between, we'll discuss on the next week arrangement for Monday, Tuesday. Right then. Okay, bye bye. Take care. Assalamualaikum.